Okay, kiddos, I'm going to go ahead and walk you through this worksheet, endothermic versus exothermic. So we have to do a couple of things, okay? So we have to underline the system in each problem. Okay, the system is just what we're looking at it, which thing we're looking at it through their point of view. Okay, number one, an ice cube melts after being left out on a table over an extended period of time. Are we looking at this from the ice cube's point of view or from the table's point of view? Because that's important. That can change our answers. Okay, so you have to underline the system. We're going to classify it as either exothermic or endothermic. We have to sketch our graph. We have to say whether our delta H or enthalpy is positive or negative. Okay, first off, please ignore any background music you may hear. My son's watching Blaze and the Monster Machines, so just ignore that if you can. So an ice cube melts after being left out on the table for an extended period of time. Well, let's look at this from the ice cube's point of view. So an ice cube is melting. So in order for an ice cube to melt, ask yourself, does heat have to go into the ice cube or does heat have to leave the ice cube for the ice cube to melt? Heat has to go into the ice cube for the ice cube to melt. So it's gaining heat. So enthalpy is going to be positive because it's gaining heat. So if it's gaining heat, does that make it endothermic or exothermic? Endothermic. If something is gaining heat, it's endothermic. Now, our enthalpy diagram. How would that look? Okay, well, we have our energy. And then on this side, that's the reaction coordinate. That's the direction the reaction is going in. Okay? If something is endothermic, what that means is the reactants will have less energy than the products, right? It's gaining heat. It's gaining heat. So the products are going to end up with more energy because the whole thing is increasing in energy. So endothermic, we're going to start at the bottom, and then it's going to go up, up, up. Then it releases a little bit, and then it levels off. So you see your reactants are going to have more energy than your products. I mean, less energy, than your products. Okay? So the ice cube is our system. Enthalpy is positive. Endothermic reaction, and there's our graph. So let's look at number 2. An egg cooking in the frying pan. So do we want the egg to be the system or the frying pan to be the system? Let's make the egg. Whoops, put on my pen tool. So we underline, thought I put on my pen tool. What's going on here? There it is. So we underline the egg. So for an egg to cook, does it have to absorb heat or is the egg releasing heat? Absorbing heat. Positive, right? If the system is absorbing heat, it's going to be endothermic. And our enthalpy diagram will look like this. Okay, there it is. Products have less energy, right? Because the system is absorbing heat. This upward curve shows that the system is increasing in energy. It's absorbing heat, absorbing energy. A match burns or ignites after being struck against a rough surface. So the match will be our system. So if a match is burning, it is losing energy. It's giving off heat. So from the point of view of the match, our delta H is negative. Okay, it's giving off heat. So that makes it exothermic. So our graph here for an exothermic reaction, okay? Remember, exothermic, it's giving off energy. If it's giving off energy, which do you think will have more energy? The reactants or the products? If a reaction's giving off energy, that means it's losing energy. So the reactants are going to have more energy than the products. Okay, remember, we start up high, and we have to go up a little bit, and then we come back down. Okay, here's why we go up a little bit. Every single reaction, even exothermic reactions, they have a small little amount of activated energy. Okay, remember that from the notes from last week. Activated energy is the amount of energy the reaction has to consume in order for it to begin. So an exothermic reaction still is going to increase in energy a little bit, okay? And that's the energy that it absorbs maybe when it's struck, right? The friction. It has to absorb a little tiny bit before it starts burning, and it gives off all this energy. So here is your graph for an exothermic reaction. The human body uses the energy provided from the digestion of food. Okay, so let's use the human body. That's our system. Is it absorbing energy or releasing energy from food? Absorbing it. That makes delta H positive. That makes this one endothermic. Okay. That makes our graph look like this, absorbing. That makes our graph look like that, right? After a while, it just becomes a habit, right? Endothermic, positive delta H, you know what the graph looks like. It just takes a little bit of practice, okay? Morning dew forming on grass and plants. This one can be tricky. Dew. This one can be tricky, okay? Morning dew. What's dew? How does dew form? You get all the water in the air, and those water molecules clump together until they form a liquid droplet of dew. So we have gas to a liquid, okay? In order for gas to turn into a liquid, does it have to absorb energy or release energy? Does it have to absorb heat or release heat? In order for a gas to condense into a liquid, the gas has to release heat. It has to lose heat. So delta H is negative, right? The gas is losing heat. Think of steam. In order for steam to turn back into water, it has to cool down, right? You're releasing heat. Steam is losing heat. So, exo. Not all exothermic reactions give off heat. Not all of them are hot, okay? That's a common mistake kiddos make. They think exothermic reaction, and they automatically think fire, hot, heat. No, exothermic just means it's releasing energy, okay? All the hot ones, all the reactions that do give off heat are exothermic, but not all exothermic reactions give off heat, okay? It's just saying the system is losing energy. So exothermic reaction loses energy. There you go. Okay, so let's continue on. Dynamite explodes. That one's pretty self-explanatory. Dynamite is a system. It's exploding. It is most definitely giving off heat. So the dynamite itself is losing heat. Exo. So our graph will be an exothermic graph where it is losing heat. Okay, simple as that. Rubbing alcohol evaporates. So we're talking about a phase change. We're talking about a phase change. During a phase change, we are going from a liquid to a gas, right? When something evaporates, it goes from a liquid to a gas. So does the liquid have to absorb heat in order to do that, or does it have to release heat in order to do that? Absorb. Absorb. Where do you suppose the heat is coming from that the alcohol is absorbing? I'll give you a hint. Skin, right? Your skin is giving off a lot of heat. So if you were to choose skin for the system, then this would be exothermic. Then everything would just be backwards. But since we're choosing rubbing alcohol for the system, it's endothermic, and it's taking in heat. Okay, so this really depends on what you choose to be the system. If you had chosen the skin to be the system, the skin's giving off heat, our delta H would have been negative, and it would have been exothermic. But because we chose rubbing alcohol as the system, okay, the alcohol has to absorb heat in order to evaporate, so it's endothermic. And again, our graph for endothermic reactions, it's absorbing, so it goes higher, 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 then levels off. Okay? So, hopefully you tried this first before watching the video. Okay? If you have any questions, I am always I'm close by to Zoom. I may not be logged into Zoom, but if you send me a message, we can log in really fast and I can answer any questions you have. But I do have open Zoom hours every Wednesday and Thursday, 10 to 11 a.m. I'm on. Just pop on in, and I'll always post the meeting ID and the password. Okay, kiddos? Alrighty. We'll having a quiz over this shortly. And happy Monday. Bye.